Quantum mechanics describes what the electrons are doing. Electrons exist within orbitals. We just spent a lot of time talking about what those orbitals look like. Most elements have multiple electrons. Hydrogen has one. So we like to specify where are the electrons in these orbitals. We do that using an electron configuration. So for hydrogen, hydrogen only has one electron. That electron is going to be in the lowest energy orbital. So that's going to be in principal energy level 1. And the only orbital available there is an s orbital. So this electron is in the 1s orbital. So the electron configuration gives the designation of the orbital, 1s, and then a superscript tells us how many electrons are in that orbital. And so 1s1 is the electron configuration for a hydrogen atom. Crazy calculations with Schrodinger's equation show that one electron in hydrogen occupies the lowest energy orbital, and this fits with lots of things that we understand in nature. Everything seems to go to lower energy. We can solve Schrodinger's equation for the hydrogen atom. We can't solve it for multi-electron atoms, but we can get approximations. The reason it gets complicated is we have additional terms due to the interaction of two electrons. So in a hydrogen atom, there's only one electron. There's nobody for it to interact with. So everything is simpler. You get even to helium with two electrons, and now you have to consider the interaction of those two electrons. And then it just gets even more complicated beyond that. But we do understand from approximate solutions that orbitals in other elements are approximately the same as the hydrogen orbitals. So the s and the p and the d and the f. So we've got two extra things that we have to consider. One is electron spin. That's that fourth quantum number. And then energy splitting of the sublevels. So let's look at electron spin. Orbital diagrams give us another way to express where electrons are. They give us a little more information, and they're more visual than an electron configuration. In an orbital diagram, we're going to use a box to represent a single orbital, and we'll designate electrons as arrows. Usually we make half-headed arrows, and they can be either pointing up or pointing down. That would correspond to a spin quantum number of +1/2 or -1/2. By convention, we put the first one in pointing up, and the second one would come in pointing down. If you looked at hydrogen atoms, though, about half of them would have that one electron spin up, and the other half would be spin down. So it's just convention that we always put the first one in pointing up. Pauli exclusion principle tells us that no two electrons can have the same 4 quantum numbers. So the 4 quantum numbers function a lot like your Social Security number, right? No two people can have the same Social Security number, at least in theory, unless, it would have been a mistake if that happened. So if you have these 4 numbers, that describes a single electron. So if you have 2 electrons in the same orbital, they're going to have 3 of the quantum numbers identical. N, L, and M sub L will be the same. The 4th one has to be different. So one would have a +1/2 spin, the other would have a -1/2 spin. So an orbital can only hold 2 electrons, and one has to have positive and one has to have negative spin. And that allows us to have 4 individual quantum numbers, or a combination of 4 unique quantum numbers for each electron. When we know the number of orbitals in a sublevel, then we can tell how many electrons could be in that sublevel. So the S sublevel has 1 orbital. Each orbital can hold 2 electrons, and so that level can hold 2 electrons. The P sublevel has 3 orbitals, each can hold 2, so we got 6 electrons. D has 5 orbitals, so it can hold 10 electrons, and F with 7 orbitals can hold 14. Let's look at helium. Helium has 2 electrons. So the electron configuration would be 1s2, and the orbital diagram would be like this. The 1s is represented by a box, and we have an arrow pointing up and an arrow pointing down. We can look at the quantum numbers for those 2 electrons. They're both in n equals 1, L equals 0, M sub L equals 0, but one is plus and one is negative. Any questions? For hydrogen, the sublevels in each principal energy level all have the same energy. So the first principal level doesn't have any sublevels, but the second one has S and P, and those have the same energy. The orbital energy only depends on the principal level. That's for hydrogen. We say those orbitals are degenerate. That means that they have the same energy. They're all the same level. Everything but hydrogen with multiple electrons, the energies of those sublevels are split. That means the S, the P, the D orbitals do not have the same energy, even though they're in the same principal level. And it's kind of complicated how that happens, but it involves charge interaction, shielding, and penetration of electron densities. And so what we see is that the different sublevels have different energies. In general, the order is that S is lower, P is next highest, and then D, and then F. So the F orbitals are going to have a higher energy than the D orbitals. Coulomb's law is, we're not going to do calculations with it, but it's important to understand it in concept, because this talks about the interaction between charged particles. So the potential energy depends on the charges and the separation. So we can look at this in terms of the nucleus and an electron, opposite charges, and R would represent the distance, average distance between the electron and the nucleus. When the charges are the same, 2 positives or 2 negatives, then the energy is positive and the charges repel each other. When the charges are opposite, E is negative and the charges will attract. And the potential energy increases as they get closer and closer together. The strength of interaction also increases as Q gets larger. Any questions? It's a little bit like magnets on the refrigerator. Put a magnet on the refrigerator and you're holding up a note from school or something, right? Sticks up there just fine. What if you put 10 pieces of paper and try to use that same magnet? What's probably going to happen? It's going to fall off, right? Did the magnet stop being a magnet? No. But 10 pieces of paper increased R, the distance between the metal surface and the magnet. Magnetic charges operate on roughly the same principle. The farther apart they are, the weaker the attraction. It also depends on the strength of the magnet. If you have a really, really strong magnet, it's going to be attracted more strongly. So if we have high electrical charges, +2, +3, etc., the energy is going to be larger, and if R is smaller, the energy is going to be larger. So electrons are going to experience attraction of the nucleus, but they're also going to experience repulsions from the other electrons, because electrons have negative charges, and so they repel each other. The repulsions cause electrons to have a reduced attraction to the nucleus because these other electrons are sort of getting in the way. We call it shielding. So the amount of attraction that an electron feels for a nucleus is called the effective nuclear charge of the electron. It's called ZF for effective nuclear charge. Do you remember what Z was? We had A and Z numbers associated with the periodic table. Atomic number. So Z was the atomic number. That's the number of protons. So Z is the number of protons. This is the effective nuclear charge. From the electron's point of view, this is what the nucleus appears to have as its charge. The closer the electron gets to the nucleus, the more attraction it experiences, because as R becomes smaller, the energy becomes larger. So there are these multiple orbitals, right? And the better that the outer electron is at penetrating the electron cloud of the inner electrons, the more attraction it'll have for the nucleus. So some of these orbitals have places that are closer to the nucleus than others, and so those are penetrating through the others. And that degree of penetration is related to the radial distribution function. So let's look at this. This probably didn't make a whole lot of sense. So here we have the nucleus for, what is this, lithium? Yeah. Lithium atom. We've got 3 protons in the nucleus. And there is shielding that occurs. So there are 2 electrons in that 1s orbital, and then this 3rd electron has to be in the 2nd principal level. So this is up in a 2s orbital. So these, in the 1s orbital is smaller than the 2s orbital. So this electron is farther out, and so as it looks at the nucleus and is attracted to it, these other 2 electrons, which I'm showing them here as points, but really they are a cloud, right? A standing wave. Those guys are interfering with the attraction that this electron experiences. Does that make sense? Here, if this electron can get in closer, it can penetrate into this cloud, then it's going to have more attraction for the nucleus. Any questions? Because of the shielding of these 2 electrons, this electron out here is experiencing a charge of about +1. It's the charge on the nucleus minus the number of electrons that are getting in the way. Here, when this electron is able to penetrate into this space, it can experience the full +3 charge of the nucleus. So here is total radial probability versus distance from the nucleus. So here's the 1s orbital. That's literally off the chart there. So this is very close to the nucleus. The 2s orbital has a small maximum here and then a node, and then a lot of it is out here. And the 2p orbital does not have a node and has this shape. So the penetration is represented by the area where the 2s and 2p orbitals overlap with the 1s, where they penetrate into the 1s orbital space. And so we see that because of the shape of this distribution, a 2s electron can get much closer to the nucleus because it is in here than a 2p electron. So a 2p electron has some significant probability out here, but it's falling off the closer it gets. And it's that distance from the nucleus is very important. So just like with the magnet on the fridge, you put 2 pieces of paper up there, fine. 3 pieces, now it starts to slide down maybe. You put a 4th piece of paper between the magnet and the refrigerator and it just falls off. A little bit of distance can make a big difference. So the 2s orbital penetrates into the 1s orbital, and so it experiences less shielding. This causes the 2s orbital to be lower in energy than the 2p orbital. They have the same principal quantum number, 2, but because the 2s orbital, because of its shape, it can get in here, it's going to have a lower energy. That make sense? So the sublevels are not degenerate. So we've got the S has better penetration, so lower energy, and then P, and then D, and then F. And the F orbitals have the poorest amount of penetration. When we get higher in the principal energy levels, the fourth and the fifth levels, the effects of the penetration become so important that the 4s orbital is actually lower in energy than the 3d orbital. And the 5s is lower than the 4d. And so we get this overlap, this mixing up, in a sense, of these different orbital energies. As we go from, what am I seeing here? The energy separations between one set of orbitals and the next become smaller beyond the 4s. As the sublevels become larger and larger, the difference in energy between them becomes less and less. And so we're going to learn a general ordering of the different sublevels, but it can vary somewhat from element to element. But we're just going to learn the one that works most of the time. Okay, so this is a general ordering of orbitals for a multi-electron atom. So here's the 1s orbital. It's got the lowest energy. 2s is next, and then 2p is a little higher. The 2s is lower because it can penetrate into the space of the 1s orbital and get closer to the nucleus. 2p is higher. It doesn't penetrate as well. The 3s orbital, the sublevels, are higher in energy, and the 2p, again, s is lower than p due to penetration. But now things are getting closer and closer together. Their 3d orbitals are higher in energy than 3p, but the 4s is actually lower than the 3d. And so now things get a little out of order. We've got 4s and 3d and 4p and 5s and 4d. And so there's different ways to remember that. There's memorization, there's this drawing a diagram with arrows, but I'm going to show you that it's actually hiding on the periodic table. Before we get to that, we have to talk about how the orbitals are going to get filled up. Everything in nature tends towards lower energy. So the electrons are going to go into the orbitals in the lowest energy combination that they can have. So the lower energy orbitals fill first, and then as you go on, you fill up in increasing energy. Orbitals in the same sublevel have the same energy. So in the p sublevel, 2p sublevel, there are 3 orbitals. Those 3 orbitals do not vary in energy. They have the same energy. Those are degenerate. Here's the filling order. And again, I'll show you where you can find that on the periodic table. Each orbital can hold no more than 2 electrons. Pauli exclusion principle says the spins have to be opposite. And another rule, Hund's rule, says when we're filling degenerate orbitals with the same energy, the electrons are going to fill them singly first with parallel spins. So the S doesn't have, it only has 1 orbital. There's not a second orbital there with the same energy. But when we get to P or D sublevels, then we have multiple orbitals. They all have the same energy. And so I think of it this way. When I was in college, I used to ride the bus. And you get on the bus, and you look around, and you don't know anybody on the bus, because there's lots of strangers, right? And so there's a couple of empty seats, and there's a lot of seats with 1 person sitting in them. Are you going to go sit next to a stranger, or are you going to take your own seat? You're going to take your own seat, right? That's what electrons do. Same energy. Do I pair up with an electron in that orbital, or there's an empty orbital, I'm going to go take that one. So they're going to take their own orbital if they can. You get on the bus and there's only half-filled seats. Now you have to sit down next to a stranger, but it's okay because everybody knows how it works on the bus. You got to sit somewhere, and you're not being rude, you're just sitting down. But if there's a whole bunch of empty seats and there's like 2 people sitting with an empty seat next to them, and you go sit next to one of them, that'd be weird, wouldn't it? They're like, what's wrong with you? Why are you sitting next to me, right? So that's how the electrons are too. Okay, so this was all probably somewhat confusing. So I have an analogy for this, and my analogy is the Quantum Hotel, a discount resort for electrons in Mrs. K's chemistry land. So, Disneyland's supposed to be the happiest place on earth, right? This is my version. I call it chemistry land. Okay, so lots of crazy things happen in chemistry land. But there's this hotel, the Quantum Hotel, and it's got kind of a funny shape. It wouldn't be good in California where we have earthquakes. It's smaller at the base, and it gets bigger as it goes up. So the first floor only has 1 room. The second floor has 2 rooms. The third floor has 3 rooms. Guess how many rooms are on the 4th floor? 4. Okay. The rooms are given letters. So on the first floor, there's an S room. On the second floor, there's an S room and a P room. On the third, there's S, P, and D. On the fourth, it would be S, P, D, and F. And so how do you keep the different S rooms straight? Well, the one on the first floor is the 1S, and the one on the third floor is the 3S. You following me so far? S rooms all have 1 double bed. P rooms have 3 double beds, D rooms have 5 double beds, and F rooms have 7 double beds. I told you things were a little strange in chemistry land. Have you ever seen a hotel room with 7 beds in 1 room? That's weird. We have rules in the hotel. You can only have 2 people in a bed, and they have to have opposite spins. Well, what does that mean? So I think of the electrons as being people. Not sure why, but I think of them as being masculine. So you think of 2 guys coming in. They don't know each other. They're sleeping in a hotel room. There's 1 bed. What are guys going to do? My experience in grad school going to conferences and talking to the guys was usually they would do some game or strength contest to decide who got the bed and the other person slept on the floor, right? Because, ew. Okay, here you're not allowed to sleep on the floor. It's a rule. We could elaborate on that, but I'm not going to. So you can't sleep on the floor. So what are these electrons going to do? So if this is the bed, right? The first guy comes in and he's going to climb in bed and he's going to sleep with his head at the top of the bed like normal people do. And the next guy comes in and he's like, I have to sleep in the bed with this guy. What am I going to do? I'm going to sleep the other way. And so we're just going to, just keep it simple that way. Okay, so they sleep head to toe. This actually used to happen back in, 1800s or so. Barracks, I know in Fort Snelling, they had these bunk beds. I've been there, and they're like regular-sized bunk beds, maybe even a little bit smaller. But 2 soldiers would sleep in this twin bed. And they would sleep head to toe because they'd fit better. And the reason they slept together like that was to keep each other warm because they didn't have any heat and it was stinking cold. So this is what the electrons are going to do. So how does this correlate to quantum mechanics? Well, the floors in the hotel are like the principal shells. So principal quantum number 1, 2, 3, 4, 5. The rooms are like the subshells, S, P, D, and F. The beds are like the orbitals. So each of these beds is an orbital. Each orbital can hold 2 electrons. Each bed can hold 2 people. Money is like energy. So as the electrons come to stay in this hotel, they're cheap. They're not here to enjoy the luxurious hotel. This is a discount resort. They're off to do other things during the day. They got to sleep like this. This is not fabulous. They're cheap. They want the cheapest room possible. So they're going to fill up that 1S room first, 2 people. Then they're going to fill up the 2s room, then 2p. And so they fill in the order of increasing energy. Any questions? So you could think of this as sort of a diagram or an illustration of the hotel. So here's the shape of the hotel. It's kind of a weird shape. It's like an upside down of that pyramid one that they have in Vegas. But here's one room on the first floor, 2 rooms on the second floor. The S room with 1 bed, the P room with 3 beds. So if you're going to stay in the 2P room, does it matter in terms of cost which bed you sleep in? No. They're all the same price. It's degenerate. So the electrons come to stay here. Let's pretend that we've got an electron in here and another electron, and we've got 2 electrons staying in that room. And now let's imagine, more electrons coming, and so that guy's going to take the first bed. The next electron coming in, is he going to pair up with that one when there's 2 empty beds? No, he's going to go take his own bed. Is he going to sleep upside down? No. He's going to sleep right side up. And the next electron would come in and take that bed. Now, the 4th electron coming in, now he's got to share, right? So he'll go upside down with the first guy, and then it would fill. And once that room was full, the guy comes in, but I didn't want to spend this much. Well, I'm sorry, those rooms are full. You have to shell out for the 3S room. You're going to have to pay more. So then he comes up here. And so even though the 3D room is on the same physical floor as 3P, it costs more. And so after the 3P is full, rather than going on to the 3D room, the electrons will opt to stay on the 4th floor in the S room. And so it's by cost, and so it's not strictly by floor. And the cost corresponds to the energy. Any questions? So the electron configuration is a little bit like the clerk at the front desk. And he's got his shorthand notation so that when the next guy comes in, he can tell them what room to go to. So he's keeping track of how many people are in each room. When we write an electron configuration, unless it states otherwise, we're assuming that this is the ground state, the lowest energy, that all the electrons are in the lowest energy. The number of electrons in a neutral atom always equals the atomic number. So if we're drawing an electron diagram, like for magnesium, magnesium has the atomic number 12. That means it has 12 protons. A neutral atom will have 12 electrons. Anybody wonder how you could have 2 negative electrons in the same orbital and not have them fight with each other or repel each other? That's like, how does that work? The parallel spins, this says parallel spins, but in an orbital they're opposite spins. It's Monday morning, my brain's not working. The spin pairing of the electrons correlates their motion and minimizes their repulsion. If you want to know more about that, we can talk about it later. So when we look at the electron configuration, it's just a list of the sublevels in order of filling, and we use a superscript to indicate how many electrons are in that level. Now this is one place where chemists do write the number 1. So krypton has 36 electrons. And so this is how those electrons would fill the orbitals. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. The 4s fills before the 3d because it's lower in energy. The electrons are going to stay there because it's cheaper than going up to the 3D room. They won't go there until this one's full. So as you can imagine, I mean, that's krypton with 36 electrons. You get down to radon with 86 electrons, you're going to have a long string of numbers and letters, right? So there is a short version. It's called a noble gas configuration, or noble gas shorthand. And so what we do here is we use the noble gases as an abbreviation. So here's the full electron configuration for rubidium. This part right here, oops, that is the same as krypton, right? Rubidium has one more electron than krypton does. And these orbitals get filled in the same way every time. So instead of writing all of this out, we can put the symbol for krypton in brackets and just write the extra electrons. So we could say, well, it's krypton and then 5s1. That extra electron is in the 5th energy level, the S sublevel. Now you can't do this with other elements, you can only do it with the noble gases. Any questions? So here's lithium, beryllium, boron, and carbon. So we're going up in number of electrons. These are the electron configurations. These are the orbital diagrams. I really like the orbital diagrams because they give us a better picture. Kind of goes along with the hotel as well. You can imagine each of these boxes is a bed, right? So there's one bed in the S room, and this is another S room. Here's a P room. It's got 3 beds. We draw those boxes together because they are the same energy. They are degenerate. They're together. So as the electrons come to stay, we get here, he takes his own orbital, his own bed, and then the next one that comes in takes the next orbital. It doesn't pair up here. They're going to fill each separately with parallel spins, and then they're going to pair up. That's Hund's rule. Any questions? Okay, so let's write the orbital diagram for argon and figure out how many unpaired electrons there are. Well, the first thing we need to do is find argon on the periodic table and identify how many electrons does argon have. 18. So argon has 18 electrons. So we'll start drawing boxes. So there's 1s and 2s, 2p, 3s, 3p. Let's see if that's far enough. Then I'm going to put the electrons in there, and I'm just going to count as I go. I'm going to count to 18. So I've got 1, 2. That second one is opposite in spin, because they're going to sleep head to toe. He's not going to move up here because this will be higher in energy. So it's 2, 3, 4, 5. Now the next one has his choice of an empty bed. These are in the same room, same cost. These are the same sublevel, same amount of energy. Or I could pair up here. So it's going to take his own bed. So what was that? 5, 6, 7. Now they're going to pair up rather than pay out more money. They're going to pair rather than go to a higher energy level. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Does the idea of the hotel help make sense of how you would fill those in? So how many unpaired electrons are there? None. So there's 0 unpaired electrons. Unpaired electrons would be those that have their own orbital, that are not paired up with another electron of opposite spin. Oh, let's do this just for practice. When we're first learning this, I think it's best to write the orbital diagram and then write an electron configuration. So let's just write an electron configuration from this orbital diagram. So 1s, and we look and see, well, how many electrons are in there? There's 2 arrows, right? 2s, 2 arrows, 2s, 2. Next is 2p. How many electrons are in there? 6. And then we've got 3s with 2 and 3p with 6. So that's the electron configuration for argon.